So first, the number 13 slide set, which was about only development length. And that was a straight development length. We said the development length is going to be given by this equation here. Equation here looks complex, but it's really easy. It says here development length is going to be equal to a constant 3 divided by 40 applied by the yield strength of the steel, divided by lambda. This lambda is going to be the lightweight concrete factor. This is equal to 0.75 if you have lightweight concrete. If not, it's going to be equal to 1.0. Square root of F prime C, which has to be in psi. I guess I repeated this psi many times now. And unfortunately, I still see people using it as in psi. So this is going to be in psi only. No psi here, an equation like this. And then after that, we have few factors multiplied by the bar diameter. So I have here bar diameter that you are trying to splice, not any other bar. Then I have a few factors which accounts for whether the rebar is top or bottom, epoxy coated or not, size of the rebar itself, and then we have the edge distance. And this edge distance can be also the spacing between two adjacent rebars. We have done a few examples. Now we understand how to do CB. So CB here, as in this example, it could be the edge distance here, or it could be the edge distance to the side, or it could be half the way between the adjacent bar, like what we're showing here. And of course, the one controls is going to be the smallest of all of these three. We have done a couple of examples. Now, we would like to see the meaning of this hook development length. All right. So first, the hook. We said that we have what we call here a standard hook when it comes to rebars. We have the 9-degree standard hook. And of course, it comes with certain dimensions related to the bar diameter. For example, the length of this tail is going to be 12 times the bar that you're trying to hook it. And this diameter D, as it says here, is going to be given as from 6 dB, which means 6 times the bar diameter, or it's going to be 8, or it's going to be 10, depends on the bar size. If you have a rebar that you bend, but you don't really extend this for 12 times dB, let's say that this number 8, so I'm going to put here quick numerical example. I'm going to say for number 8. This 12 dB is going to be equal to 12 inches. Let's say you decided to make it 6 inches, or this is just what happened, at the side. You cannot really consider it to be 9-degree standard hook. So whatever equations is going to be applicable to a hook cannot be used for a case if you use this to be 6 inches instead of 12 inches. So this is going to be a minimum of 12 inches. So if you'd like to make it 13 inches, it's going to be okay, but nothing less than 12 inches in the case of number 8. Here is the 180 degree standard hook. So the rebar is going this direction and it goes back in the same direction. That's why we call it here 180 degrees. And the extent beyond this point is going to be 4 times dB, and it has to be greater than 2.5 inches. So actually, out of this few details, you can extract lots of information about the size and the use of 90 degree standard hook and 180 standard hook. This one here, this is what we call 135 degree standard hook. We use this a lot in columns and from time to time in beams. This is what we call here cross tie. So the whole thing here is called cross tie. As one word. In the ACI code, recognized to be one word. But when you do this, you see here the red means it is that you have an issue with the spelling, but in the ACI code, you have it as one word. So from a certain given distance here or location, I'm going to say here from certain location that you'd like to develop the rebar. So you can either go with the straight development length, L sub D, that we worked on last time from slide set number 13. In many cases, this length is just too big and you don't have a space to make it that big. So in a case like this, you can do the 180 degree or you can do the 90 degree. And in this case, this length from this critical section to the end of the hook, which means to that point of the hook, is going to be called LDH. So the other one that we used here, that was just LD. If you look here at this equation, LD is going to be the straight development length. And this length here is going to be much larger than that needed for LDH. So I said, okay. Here's the equation for LDH. Let me put also the other equation here for just L sub D. You see the equation? Yeah, it's going to be like some factors multiplied by dB. I understand that, but it's going to be much simpler than that for the straight development length. It gives you here a constant of 2% times psi sub E, and we know psi sub E is going to be that for the epoxy coated. F sub Y divided by lambda square root of F sub C, which means same factors as the factors that you're looking here at. So I can say this can be the same as this. And so this constant is going to be 2%. So all of that, we're just going to be taking this psi sub E. So okay, good. They made the equation simpler. And they say this psi for the epoxy is going to be only one value. If you remember for the straight development length, we have 3 values, 1.0, 1.2, 1.5. And here I have only 2 values. It could be 1.2 or 1.0. So the equation here is much simpler. And again, the lambda is going to be the concrete, the lightweight concrete factor, 0.75 or 1 for normal weight concrete. In the past, for the straight development length, we say it's going to be minimum of 12 inches. In a case like this, for the hook, it's going to be minimum of 8 dB or 6 inches, whichever is larger. LDH, I have here some multiplication factors. I have some factor multipliers, if you like to call it this way. It says here you have this multiplier, which is 0.7, is going to be for number 11 rebars or smaller, which means for almost all rebars that we use. With the side cover, is going to be less than 2.5 inches. And 9-degree hook with the cover on bar extension beyond hook, not less than 2 inches. So, okay. Also, you have another multiplier for 9-degree hooks only. When you have number 11 and smaller, once you put it in ties, and the ties can be perpendicular to the bar that you're trying to hook, and they give a certain spacing and cover. You have another factor of 0.8. This one you have 180-degree hook, number 11 and smaller. So you have one specific number, 9 degrees standard hook. The other one's going to be specific for 180 degree standard hook with certain spacing. The same reduction factor for L development can be used here, as you see here. But for this LDH, You don't really want to use it because the hook is short anyways. We are talking about here 10 inches, 8 inches. Yeah, so it is not worth it that you'd like to use it here. We have an example. Let me tell you the story of this example. This is a column. So this is here, a column, right? Here's the end of the column. And they have the top and the bottom bars. I need to end them. I need to end this rebar into the column. And this column length is critical because only 24 inches. So someone here says, why don't you just keep it straight? Because bending the rebar is going to be like a hassle. It's going to be a cost. So I just like to keep it straight if I can. So the problem is when I run the analysis based on this equation that we used last time, if I run this equation here and the length was within 24 inches, I'm going to say maybe 23, 22 inches because I need those to be a cover. I'm just going to keep it a straight bar. If it happens that this rebar, the L sub D needed, is going to be, let's say, 30 inches, it means the rebar is going to be like this. This is not good because I cannot have the rebar sticks out of the column. In a case like this, I'm going to say, you know what? Maybe I need to try the hook, L sub DH, and maybe I can just end up with something like this instead of having a straight bar. So again, if the straight development length is less than this available length, which means maybe 22 inches, not 24, because don't forget, you need to have here a cover, concrete cover. If it's going to be within, let's say, 23 or maybe 22 inches, that should be fine. Just keep it straight. If it goes beyond this 22 or 23 inches, I may need maybe to provide a hook. And LDH is going to be measured from here all the way to the end of the hook. Someone's going to say, how about if I try also LDH and the length was larger than 24 inches? Meaning hook is going to be looking like this. It's going to be sticking out. It's going to be something like this. I'm going to say, in this case, I need to make the column larger because there is no way. Or maybe work with the rebar size, maybe reduce the bar size. The reason I'm saying reduce the bar size because this LDH is going to be based on D sub B. So let's say that I have number 8. If I change it to number 6, it means I'm going to reduce it by a factor of 3/4, right? Because if number 8 is going to be 1 inch, for number 6 is going to be 3/4. So I'm going to be reducing this LDH to a factor of 3/4. So it could be a good idea to change the bar size, not just keep a very large bar size.
Professor?
Example, yes.
So the hook doesn't necessarily have to hook onto other rebars. It's just better like seated into the concrete.
Yes, to end the rebar.
Okay.
Yeah. If you're going to put two rebars next to each other, we're going to be calling it splice, which we didn't do yet.
Okay. But yeah, so the hook is not hooking onto rebar at the end or anything?
Oh, you mean hook here, like a rebar like this? Yes, of course, you need a rebar like this. If you're talking about this is going to be the hook, and then I need to put a rebar, I'm going to say to put a rebar here, I'm going to say yes. Rebar like this, correct?
Oh, okay.
Okay, correct. In this problem here, it says determine the anchorage or development length required for tension for the top rebar, which means for this rebar here, the top one. For the conditions shown in the figure below, yeah, understand that. Use concrete strength 3000 psi, normal weight concrete, lambda is going to be equal to 1. F sub y 60,000 psi. Uncoated, which means no epoxy. Your psi sub E is going to be equal to 1. It's going to be number 8 bars or top bars. So the top bars here is going to be 3 number 8, right? And I see here that I have more than 12 inches of concrete. So it's going to be okay to use it as top bar. Assume side cover on the main rebar of 2.5 inches. So the side cover is going to be 2.5 inches, and this is going to be critical when it comes to the CB value. If you guys remember the CB value, it's going to be where it comes into picture. And inspect the use of 180-degree hook and compare. Meaning, try to use LD only. Just try to use L sub D. If it didn't work, try it 180. And just do comparison. See the big difference between the use of 180-degree hook and between the use of just straight development. If you are the contractor, you'd like to keep it straight because providing a hook or bending it is going to be a cost. It's going to be work on the steel. But just have it straight is going to be simple. You're not doing anything. You just cut the rebar and put it in place. First, this factor, if you remember that this is what we call K sub D, which is this factor here. 3 divided by 40, F sub Y divided by lambda F prime C. Let me get to this factor. Here we go. K sub D, which means this factor here. From this table, when you have 3060, it's going to be 82.2. Okay, 82.2. I have top rebars. When I have top, it's going to be 1.3. For the rebar size, when I have number 7 larger, it's going to be number 8 now. This is going to be 1.0. No epoxy coating, it's going to be 1.0. As I said, normal weight concrete is going to be lambda of 1.0. Let me remind you with this. Yes, okay. About the factors. I have here psi sub T times psi sub E less than or equal to 1.7. Okay, let me do this check. Yeah, less than 1.7 because I have 1.3 and 1.0. C sub P based on the given information here, cover to center and or center of the rebar to the cover. And we have done this in the past. We went through this already. So I'm just going to show you this. Here's the CB analysis that we have done, which means from the center of the rebar to the edge of the concrete in any direction, let's say to the top, to the side, and half the way to the next or adjacent rebar. Yeah, a second. So here's the CB analysis. At the end, we ended up with 2 inches. So, okay. KTR, we said usually for ties, we're going to assume this to be equal to 0. And then CB plus KTR divided by the bar diameter, we said it's going to be maximum of 2.5. Now it is equal to 2 in this example, so I can just go ahead and use 2.0. I'm using here the long equation, and I'm getting 53.4 inches. I need to check if this is going to be larger or smaller than 12 inches. If it is larger, then I'm going to say maybe 54 inches. This is good. Now, the length of the column is 24 inch, and what you have here is 54, meaning the rebar is going to be like this. So the use of this straight development length thing in a case like this doesn't make any sense. You cannot really do this. You see, this is, I mean, physically it doesn't work this way. So I cannot really do this. So maybe I need to put maybe 9 degree, 480 degree hook. Just because the length here is just too much. This LD is not within the column. It's actually 54, and the column length total 24 inch. So I said, well, let me try here the equation for the hook. Development length. Here's a simple equation. It's going to be 2%. No epoxy is going to be 1.0. F sub y, 3000. Bar diameter is 1. Let's say 21 inches. Actually, 22 inch, it could be good. But you know what? I have some reduction factors. It says here, when you have number 11 or smaller, and then you have side cover of more than or equal to 2.5 inches, I can do this. I can do a reduction of 0.7. So I said, okay. I don't have reduction factor for the 180 degrees. I said, okay, now I should be able to use a 0.7. So I use a 0.7. Now all what I need, let's say maybe roughly 16 inch for practical purposes. So I'm not gonna call it 1533. I'm gonna just say 16 inch. I said, okay, now this is gonna be 16 inch or 1533. Provide that I am gonna provide you a cover of 2.5. Now, do you think with 15.33, would I have enough cover if I'm gonna be taking this all the way to the end? I said, well, let me test this. I'm gonna say here I have 24 inches. If I'm gonna bring the bar anyways of the hook all the way to 2.5 inch, this distance, which means from here to there, is gonna be how much? The actual distance. Let's say this distance here is gonna be equal to 24 minus 2.5. How much is that? You can say here 24 minus 2, 22, 21.5 inches. So, okay. In reality, this is what I'm going to be providing. Meaning, I'm going to be taking the bar all the way and just keep 2.5 inch cover. And in such case, the actual LDH provided is going to be 21.5 inch. And the required is going to be 15.33. So what I provide here in terms of the LDH was larger than needed. So I should be fine. In some cases, let's say if the needed length is 20 inches, you say 20 inches needed. Let's say this different example, right? You say, I need here 20 inches. But to be able to use this reduction factor, I need to have 2.5 inch cover. So I'm going to say, let me put here the 20 inch plus 2.5. I'm okay. Problem is going to happen once this LDH needed is going to be larger than 21.5. Let's say LDH needed for number 11, I need, let's say 25 inches. 25, the bar is already out of the column. This is not a good idea. In a case like this, definitely I'll reduce the bar size. Why? Because look at this equation here. When you reduce the bar size, LDH is going to get less. So one of the ways that we do it, one of the tricks, that now we're going to play with the rebar size. The trick that was used here is to provide a side cover to be 2.5 inch or more. Once you do this, you can reduce by 0.7, 70%. This loss of reduction, 30% is loss of reduction, just because I provide here enough cover. Any questions?
Yeah, Professor, I have one.
Yes.
It was just like the wording. It says that there's no reduction factor for a 180-degree hook. But aren't we using a 180-degree hook?
We are using 180-degree hook, but we have ties. Don't we have ties in the problem?
Oh, okay.
So if there is no ties, you can't use this.
Okay. And then maybe I just didn't understand, but like, why can't you just shift the hook to the right? Like, is there a right limit to the hook as well?
Does this make sense now? Because
Yeah.
once you see here sense, you feel that, oh, in this problem, there is no stirrups or ties, correct? It should have been if there is no ties, stirrups or ties. But in our case, we have ties. So I should be able to use this reduction factor.
I see.
Now,
Yeah, no, I
now
didn't.
your second question. No, the wording, you're right. I mean, this should have been there. What's your second question?
No, I was just saying I didn't see that we had stirrups originally. But
Okay.
so the second one was just, why can't we just move like the hook to the right, or the regular LD? Why can't we just move it further right? Assuming there's
To
a
provide more
there's more
cover,
beam.
let's say to provide more cover. And
No, just keep like like if it's too long, why can't we just shift it right but still keep the same cover?
Okay. In construction, the standard way of building this is going to be taking this rebar all the way to the end. It's just much easier for construction. If you
Yeah, I
start here to
understand.
give him a dimension like here and just keep it, let's say, to here. Let's say I am planning to do it like this, right? And bring it a little bit to the right. I brought this to the right a little bit, meaning give it more cover. Is this what you're saying?
No, I'm saying keep the same. Like you were saying, sometimes the hook, if it was too long, it'd be sticking out the other end of the column. So
Which,
why couldn't you just shift it right?
because you need LDH from the face of the column. This LDH
Okay,
here, the whole theory here is measured from the face of the column. This is at the point that I don't need the hook or the rebar to where it ends. You see here,
okay.
LDH is measured from this face. This is gonna be the critical section.
Okay, so we
Edge.
don't want the length of that rebar to go past that point.
As
that
it
what you're
point to the
saying?
right. No, we want
Yeah.
it to stick in the column, to be embedded in the column by LDH, measured from this critical section, which means the face of the column. Let me take you back here. You see this in this example here, or this illustration, LD minimum is going to be measured from the critical section to the end of the bar.
Okay,
So this is going to be my critical section, to start from which I'm going to be measuring the bar inside the column to develop the bar in the column. So all the measurement is going to be taken from this critical section, from the face of the column. So when I look at this one here, I'm going to say, okay, where is LDH? I'm going to say LDH is going to be measured from the face of the column. So this LDH plus 2.5 inches is going to be smaller than or equal to 24 inches. I'm good.
Gotcha.
The problem that may happen if you add LDH needed or required plus 2.5 inches and you see the rebar sticking this way. So you're going to say, I cannot do it this way because it's going to be measured from this critical section. So the bottom line here is, where is the critical section? And start from which you're going to be measuring for this LDH till you stop the rebar.
Okay. And then did based on like that diagram on slide 8, do we need the development length on both ends of the, yeah. So I understand what you just said. Just a further question, like, do we need the development length on the right side as well, that LD minimum?
Yes, you'll need it. Yes, absolutely.
Okay, we need both of those.
Yeah,
Okay.
but you know what? This is a beam which is just extended.
Right.
So in a
So
case
that
like
that
this,
one you're not worried about.
I'm not worried
yeah.
about. I can just provide the length I need. The whole problem happens when you have limited space with the rebar.
Gotcha.
This is
Thank
why in this section I'm just talking about, if you remember the slide set is all about, started with the new thing, the standard hook. So for the straight bar, I mean I'm okay, just, I mean, this gave me maybe 30-foot beam. So when you stick it 58 inches, 6 feet, 7 feet, 8 feet, I should be fine. The problem is getting inside the column, at which you don't have enough space. You know?
Thank you.
No problem. All right, now splices. Splice is going to be a complete different issue. Splice means Lapis Splice. This is the reason that we go to splice. Lapis Splice. What does it mean by Lapis Splice? It means I'm going to be taking one rebar, put it next or adjacent to another rebar, and that's it. No welding. So these two rebars are not welded to each other. They're just next to each other. So what happens when you put here some tension, like this tension force, the stress is going to be going to the surrounding concrete and then get transferred to the other rebar, coming back to the rebar. So if you put here a force, let's say of 10 kips, you're going to end up with the same force here, 10 kips. So what happened? The stresses, all the stresses, is going to get transferred to the surrounding concrete and then back from the surrounding concrete to the other rebar without welding it. If you weld them, it's going to be called welded splice. If you put a coupler, I don't know if you guys familiar with couplers or not, or coupling system, it's going to be a different story. Let me Let me look for something here for quick. I'm gonna say Rebar couplers. Here's some rebar couplers. If you just look for it, here's a rebar coupler. You put on rebar from one side, other rebar from the other side, and then you tighten this. Sometimes it's by gripping system. Look at this system here. Look from where. We're not running any commercial here. Look at the rebar here, how it's coupled. This could be a threaded rebar at one end. Let's just look at the pictures. You see the way it works? You have a thread, coupler, and then you put them all together. Here's some pictures. Look at this. It looks like a pile. Look at this picture. Very interesting. You see here, you have rebars sticking out of this column or this pile. And then it seemed that they were short. Something happened to them. Now what do you want to do? They'd like to extend them. So they just put this coupling system. They put this coupler and then extend the rebar. So if you have a problem with a rebar that you'd like to extend, you can simply use a coupler like this. Look at this coupling in the column. This coupling system. Like in this picture here. You'd like to stop the rebars and start new rebars. So easy to just add some of this coupling. And look at this section here through the coupling system. It's gonna be very interesting. Look at this picture, it looks good. Look at this. I have here a few options. Here's a big circular column, like spiral column. I'd like to put this column attached to the bottom piece of it. So you have the column at the bottom, you'd like to extend it. If you want to do splice, like regular splice, what's the regular splice? I'm gonna say like Lapis Splice, like this. The length of this rebar could be 8 feet or 7 feet, which means like 1 story high. This is gonna be too much, right? No one liked this. I mean, this is gonna be kind of crazy. So in a case like this, maybe the use of these couplers is gonna be a very good idea. Because the problem when you have lots of rebars next to each other is gonna be really congested and you're gonna have trouble in putting the concrete here. Just imagine that between each one of this rebar and the other, you're gonna have another bar that you're trying to splice. You're gonna have lots of rebars in the same place. This is not gonna be a good idea. I mean, it's gonna be too bad if you do this. Look at this here. Here's a pile, you'd like to splice the rebars. So sometimes we use couplers, sometimes we do welding. Here's a column, right? And you see here, you don't really need to put 2 rebars next to each other. And sometimes it's just cheaper if you do this way. Because don't forget that each one of these couplers is gonna be at least like $5, $6 for a piece. It's gonna be a lot, especially when you have tons of rebars. So in many cases, just cheaper if you can do it with a Lapis Splice. And also think about threading 1 rebar and try to put the coupling system. This is gonna be also a cost. It takes time and effort. Just having the 2 rebars next to each other is the easiest. Okay. The Lapis Splice or the lap length is so simple. You just take 1.3 times LD. You don't have this Lapis Splice length for the hook. So it's gonna be only a multiplier of the LD, the development length that we know how to do. So after you do the long equation, you have this multiplier of 1.3. That's it. Now we are done with the splice length. And as it says here, splicing may be accomplished by welding, mechanical couplers, or by lapping bars. So I'm lapping bars. So I can do mechanical couplers like the one I showed you. Let me show you here. Here is the rebar lapping, right? You just put them next to each other. Or you can do couplers, or you can do welding. Of course, welding is gonna be a cost. The cheapest option is gonna be just lapping it. Second option is going to be welding. Third option is going to be the mechanical couplers. I have this example. It says simply supported uniformly loaded beam requires number 7 bars for tensile reinforcement. Effective depth 18 inches. Determine where the bars may be stopped. F prime C 4000, F5 60,000. Assume there's no excess steel, which means whatever is needed is provided. There's no reduction factor. Assume normal weight concrete and that the stirrups extend to the end of the beam at the support. The bars are uncoated. There is no coating, no epoxy coating. There is additional 12 inches that you need to provide according to this section here. So according to this section, it says the code is asking you here, if you like to stop a rebar at any section, you need to extend it for at least the distance of the depth for 12 inches, 12 dB, let's say for number 8. Here's our beam. In this beam, I have 6 rebars at the bottom that I need them for tension. The span is 24 feet. Here's the moment diagram, which is also the same as this moment diagram. Now, is this the demand or the capacity for this moment diagram? You can say, well, this curve is going to be for the demand. This is going to be based on M ultimate, right? Which means W ultimate L squared divided by 8. And it says here, whatever reinforcing is provided is exactly what is needed. Required AS is going to be the same as a furnished, which means a provided AS. Meaning, if I'd like to take this curve and call this to be M ultimate, you can say, how about the capacity? Where's phi man? You can say phi man is going to be exact same value as M sub U. We're at, you can say right here at this point. So right here at the maximum point, at this point here, this value is going to be what? Phi man. This phi man is going to be the same as M sub U at the point of maximum moment. We did not provide extra rebars. Whatever is needed, we provided exactly. Any questions on that? You're good? We understand the moment diagram. We understand the top value here is the same. Phi man is the same as M sub U at this location. So this key over here, the maximum M sub U, which is going to be the same as phi man as a capacity. So, okay. Now, I'm going to come here to this diagram and divide this phi man into 6 equal sections or segments. Look at this. 0 to 1. Here's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 3 equal sections. Meaning, I'm going to be taking this phi man divided by 6. Let's say that this phi man is equal to 60. It means each one of these gaps or this segment is going to be equal to 10. 10 times 6 is going to be 60. The reason that you are going to be dividing it into 6 segments because I have here 6 rebars. Therefore, this moment value from here to there, right, which is the same as this moment value, which is from here to there for each segment, is going to be equal to phi man for 1 rebar. If this makes sense? If you have 6 rebars, they provide you a moment capacity of 60 kip-foot. It means each rebar is providing 10 kip-foot. If I'd like here to look at a very simple numerical example. Any questions on that? Yes, before I move forward. This here's going to be the total moment, demand. This going to be the capacity. This line is going to be the capacity, right? And each one of these segments or value is going to be whatever that each one of this rebar is supporting, is providing in terms of fee man. So okay, good. Now I have the 6 rebars. The question is, should I keep them straight from the beginning to the end? You say, okay, let me draw here 6 rebars. Here's one. Let me do it in 2s. You say, here's 2 rebars. Another 2 rebars next to each other. Then I have, here's other 3 rebars. Questions. Are they in the top of each other in reality? Yes, no, in reality they are next to each other. But I decide to put them like this, just because I can put them on the top of each other. I mean, it's not going to be easy to understand, right? You're going to say, well, I see only 4 rebars. So I'm going to say now I have 6 rebars. Each one of this line represents 2 rebars. Say here, I'm going to have 3, 2 rebars. And what rebar? It says here number what? Number 7. So I have 3 pairs. Okay. Can I keep him straight from the beginning to the end of the beam? Is this okay? Do you think my beam is going to be safe? Say yes. No problem at all. You can just put 6 rebars here. You just cover it, because when you get to the point of maximum moment, you'll provide enough fee man for it based on this 6 rebars. Now the problem is, I'd like here to save some weight of the steel, some rebars. So I don't want to keep them all straight. So what I'd like to do, I'd like to cut some of them. I said, okay. It looks like to me, it should be fine to keep the first 2 here, right? So this, the first 2 is going to be from here to there, right? This could be the first 2 rebars. You follow me? So yeah, good. And then this 2 rebars that you're looking here at, gonna bring him to here, right? And I can cut them short because I don't really need them here. Look at this. You have lots of moment capacity, and the demand is gonna be within this curve. So I decided whatever I'm gonna do here on one side is gonna be the same on the other side, but I'm gonna be working only on one side. I decided just to cut this rebar here. I'm gonna say, okay, 2 rebars, I'm gonna stop him here. Is this okay? I said, well, yeah, because look at this. I'm gonna drop a line like this. This where you don't have the first 2 rebars on the top. You're fine. Why? Because look at the moment capacity. This can be your moment capacity diagram, and this can be your demand. If your demands can be within the capacity, you're fine. So I'm gonna say, how about the second 2 rebars? Second 2 rebars, I'm gonna say, well, if this give me the first 2, I guess I also should be able to move them a little bit this way, right? Here's the first 2 rebars. The second 2 rebars, I'm gonna stop them right here. Does this make sense? How about the last pair? The last pair, I'm gonna just take it all the way to here. Look what I've done. Just look at this side, only this side of the beam. Whatever that we do to the right side, we can just do it on the left side. Look what happened. If you cut a section right here, in this location, how many rebars do you have? You can say I have 2 rebars, only 2. Am I good? Do you have any problem with the capacity versus demand? I'm gonna say, look at this. Here is the capacity, here's the demand. So the demand usually is gonna be lower than the capacity. Once you hit this point, what would I do? I'm gonna provide the other pair. Now I have 4 rebars, and they have enough capacity more than the demand. Once I come to this section here, this is coming crazy, all right? Because here the demand is gonna be equal to the capacity. So in this location, I'm gonna have 3 pairs. 1, 2, 3 times 2 is gonna be 6 rebars. It covers the demand. When you look here at this diagram, you're going to say this is now becomes the capacity diagram, and this becomes a demand diagram. My job is to keep this demand to be within the capacity. So, okay. Also, the code tells me one thing here. He says, this is true, you can bring it to here, but guess what? What happened if the moment demand shifted a little bit? So what the code tells me, you need to keep it a little bit, be generous. Don't make it very tight, right? Give it a little bit of room, which means this rebar needs to be extended here, and this rebar needs to be extended here. Now the x-axis is going to be dimension like in feet. Remember, this is going to be the beam span. And the question is, how much is this distance that I need to leave? I'm going to say, you know what? Let's go here back to this. I'm going to say, in this code section 12.10.3, it says extend the rebar beyond the calculated distance by greater of the depth d or 12 dB, meaning this little distance, meaning from here to there, right? Is going to be 12 dB or d, the depth d. Now, which distance am I talking about? Let's say distance from here to there, this distance. To there. Where does this come from? I'm going to say from the code section. Where is this at? I'm going to say right there. This code section 12.10.3. So, okay, now I understand. I cannot just stop the rebar when the demand equal to the capacity. I need to extend it a little bit. It is very normal in practice that we just say 12 inches, just extend the 12 inches. Because most likely you work with the rebar is going to be less than number 8, so you just say 12 inches. If the beam is really deep, like 18 inches, I'll just extend it to 10 inches. It's going to be 1.5 times the depth D. Don't forget that you have also AS minimum, right? When you have AS minimum, it means that you cannot really cut off the rebar down. You need to leave a little bit of rebars. So at any section of the beam, it's true that you may not need the rebar, but you know what? You need to keep the minimum reinforcement. So then I start by saying, okay, let me cut 2 rebars here, 2 rebars there, 2 rebars there. I'm just assuming that 2 rebars should be enough because someone's going to come back here and say, how about this section here? Do you have minimum reinforcement satisfied? You say, you know what? Let me check. This is the reason that you're doing here this AS minimum, the standard that we do in beams. I'm going to try here 2 AS minimums, and it turns out that I will keep at least 2 rebars here, and this 2 rebars give you 1.2 square inches, and what I needed as minimum is 0.94, so I should be fine. Cutting this into 3 pairs should be fine. This gives you the conclusion. I have no problem with the minimum reinforcement needed. Now, I need to figure out where is this location happens exactly and just extend it. So the equation for this curve, this is going to be second degree parabola, and the equation between x and y, which means between the moment diagram and the distance, is going to be following this equation. Here is x1, right? If you remember, this is going to be x1. What is x1? It's going to be this distance, x1, and this is going to be y1. So here we go. Here's x1, y1, x2, y2. And this should be here x3, and the y is going to be the total moment. And this x3 is going to be equal to 1/2 of the beam span. Okay. Here's the equation here controlling x to y. You say when you take x1 divided by L over 2, x1, and this is y1, the squared is going to be equal to y1 divided by the total y, which means the total moment. And instead of calling it to be the total moment, I'm going to say, you know what, let me call it by rebar. Instead of having a value for the moment, I'm going to just call this y to be what? 6 rebars. And this y2 is going to be 4, which means 4 segments, right? 4 rebars. And this y1 is going to be equal to 2. So if you like, compare here x1 divided by 12 squared, because it's going to be 1/2 of the span, is going to be equal to 2 rebars divided by 6 rebars. Why? Because it's going to be y1, 2 divided by 6. And this x1 is going to be just the distance, which I'm after. Because my whole problem here, when I'm looking at this and the way that I've done it, I'm gonna say, am I gonna be doing this graphically? Answer is no. We need to have some analysis for it. So how do you come up with this location just extended beyond that is gonna be 18 inches or 12 dB? I'm gonna say the way to do it, I need first to figure out the distance from this point to the center, which is called here x1. Now it makes sense. And understand that this is gonna be here second parabolic degree for the curve. So I should be able to say x1 divided by 12 squared is going to be equal to y1 divided by total y, which means 2 divided by 6. That's exactly what we have done. So I said, okay. This x1 from the analysis turned to be, let's say, roughly 7 feet. I need to extend it by 18 inch. You remember this equation? 18 inch or 12 dB is going to be 18 inches. So I'm going to be adding this 18 inch, which means 1.5 foot plus nearly about 7 feet. It turns to be 8.43. You know what? I'm going to call it 8 feet and a half. If you do construction, you're going to just call this 8.5 feet. Now understand. If I'm going to go back here, I'm going to say, you know what? This length from here to there, which means x1, this x1, according to the analysis, x1 is about 7 feet. So I'm going to say this x1 is 7 feet. From this point to this point, 7 feet. This distance is going to be 1.5. So 1.5 plus 7 feet is going to be 8.5 feet. So the first 2 rebars here, I'm going to be cutting them at 8.5 feet from the center. Therefore, the total length for the first couple of rebars is going to be equal to 8.5 plus 8.5. Total rebar length is going to be 17 feet. This makes sense. So it's going to be 8.43, meaning 8.5. It's going to be from one side. And here's the first 2 rebars. I'm going to put them from here, this side, to here. Why did I extend it beyond this X point a little bit? Because it's going to be 1.5 feet. Second 2 rebars is going to be here. Of course, it's extended all the way to the end, right? Can I put them right here? This 2 rebars is going to be right here. The last pair is going to be all the way to here. And in the last pair, I'm going to have the issue of the column, so I may have to provide a hook, like what we have seen. Now let's try here the second pair of rebars. Let's say it's going to be x2 divided by 12 squared. It's going to be equal to y2 divided by y. Now it's going to be for the 4 rebars. Why? Because this point here is going to be 1, 2, 3, 4 rebars. Okay. The distance turns to be 9.8. I need to have 1.5 feet to it. It's going to be 11.3 feet. In actual practice, I'm just going to do it to be 11.5 feet. I said, okay. Also, this L sub D needs to be less than the 8.43 that I started with, meaning another check that I need to do, which is, if I may go here, let's say this x1, it needs to be more than L sub D. I'm going to say what L sub D? I'm going to say L sub D that you guys used to use. There shouldn't be any problem with that. So I said, okay. Let me try here to find out L sub D for this rebar. I'm going to say this exercise here, I don't really need to go through it in details because you guys now are aware of it. You have done it here a few times. So I'm going to figure out this L sub D. At the end, L sub D equals 26.5. 26.5 meaning like 2.25 of a foot. I don't have a problem because the length x1 is 8.43 now. So I should be fine. So I was able here to stop the rebar at 8.5 feet from the center of the beam and turn out to be greater than L sub D from the center of the beam. So I should be fine. Any questions? It's your time to ask. I'm done with today's lecture. So.
Yeah, Professor, a quick
Yeah.
clarification. So the L sub D is like there's one for the column, and then this is just a separate calculation for a beam. Is that right?
L sub D, this is for any rebar at any location of the beam. Whenever that you don't really need the bar, you need to extend it beyond that point. For example.
Okay, so anytime you shorten a bar, you need to make sure that it's still a minimum L sub D, basically.
Exactly. Exactly.
Okay.
So from this point here, from this point, for this rebar to stop it, I need to extend for L sub D to be able to take the bar or the tension out of it and bring it to the concrete. And you need the distance of L sub D. So here now, this give me the section of maximum moment. Now I need to stop the bar. I cannot stop it until I have enough distance to take the stresses out of it and deliver it to the concrete, which is going to be L sub D here. It is true that I have
Okay.
some moment demand that I'm working with, like demand versus capacity, right? Which means this curve here, right? That I'm working with based on this X1 and then D distance or 12 dB. But also I want to be sure that this is not smaller than L sub D.
That makes sense. Thank you.
No problem. Any questions? Are we good? Right. I'll post this evening. I'm gonna post a homework on the development plan. And between slides at 13 and 14, we have enough examples. And I want you just follow the examples. All right, if there's no questions, I'll let you go.
Thank you, Professor. Have a good week.
Please go ahead and sign out in the chat room.